Hey folks, it's time to put some of those ideas we talked about last time into action. We're going to take those methods of graphical solution and think about a particular problem. And I'm just going to steal the context from the book. So our problem here is the idea of having a small pond and it's stocked with two different types of fish, trout and bass. And the idea is both of these fish have the same food source. And so these are two hunters essentially who are competing with each other. So we have two different species, and those species are competing for the same food source. And apart from that, probably don't interact. And we're asking the question, can the populations coexist? Can we expect to have both species survive in that pond? So to start, we should introduce some variables. So we're going to call x of t the number of trout and y of t the number of bass, and they're both continuous functions of time. And so what we want to do is describe how they change with time, and that means differential equations. Yay, it doesn't get more exciting than that. So let's think about the trout, and we're thinking about the rate of change of trout with time, so that's dx dt. Now, if there were no bass present, let's think about what happens to the trout, right? If there are no bass, in other words, y is 0, then I would expect the trout to breed and to eat food. And so over time, their numbers would increase. And if I just take the simplest population model we've discussed, I'm going to say that the rate of change of the trout is proportional to how many trout I have, right? And that constant of proportionality, I'm just going to call it an A. And that, just to be clear, I'm going to take A to be greater than 0, because I'm going to assume that when there are no bass around, the trout are just going to feed and they're going to breed, and so over time the number of trout will grow. And A is that fractional growth rate that we've talked about many times before. But if there are bass around, then I expect that growth rate to be decreased by the competition, right? So I expect the rate of change of the number of trout, the rate of change of x, to be decreased when there are trout around. When there are bass around, when the other species is around. So this is the idea of the competition that's happening, right? So the competition is going to multiply in this, not multiply, but is going to subtract away from this growth rate. So left to their own devices, the trout will grow, but when the bass are around, the interaction between those species will lead to a reduction in the growth rate. Maybe that's a reasonable model as it is, but we're going to go to a step further and we're going to throw the number of trout in there too, because they're both competing for the same resources. They're both competing for the same space. They're both competing for the same food. And so it's that interaction between them that perhaps is the most important thing here, right? The growth rate's going to the growth rate of the number of trout is going to decrease because you've got bass eating the food, but also because you've got lots of trout. So that interaction term is going to be important here, and I'm going to take A and B to be 0, so this subtraction is really reducing the growth rate, whereas this term is increasing the growth rate. So this is what happens to the species by itself. This is what happens because of competition, and because we haven't said that there's any fundamental difference between these hunters, it makes sense that we're going to take the same setup for the rate of change of the number of bass, because I would expect the number of bass to grow left to their own devices, but that the interaction between those two species is going to lead to a reduction in the growth rate, and that's really what we've got here. So the competition is the second term, and what happens when the species is by itself is the first term, and these are our differential equations to describe the competition of these two hunter species. And so let's turn to the ideas we've got of graphical analysis and make sense of what's going on here. And I'm sorry, I realized I've used different symbols from the book, so instead of calling those C and D, I'm going to call them M and N. So the first one is M and the second one is N, and then you won't be confused when you look at the book. M and N have to be greater than 0. So let's look at this system, and when I go to the next page, I'm going to notice that I can factor out an x from the first equation and leave a minus by, and from the second equation I can factor out a y and leave n minus nx, and that's how I'm going to rewrite the equations. So here we go, we've got this setup, we've got A and B and M and N all being constant and positive, and we need some equilibrium values. Because as we saw last time, equilibrium values are the key to finding the behavior, because we look at what happens around the equilibrium values. And remember, the equilibrium values are where where the rate of change of x and the rate of change of y are both zero. So from the first equation, we see that either x is equal to 0 or a minus by is equal to 0. And this is the way I'm always going to solve them, and this is the way you should always solve equations in this and every other course. If you start dividing by things, you'll lose solutions. So we don't divide by things, we factor and then say, okay, this is a product of two things, one or the other of them must be 0. The first one tells us that x must be 0, and then equation 2 tells us that x is 0, so we've got m minus n times 0 is equal to 0, and that's m times y is equal to 0, and m's a positive constant greater than 0, so I see there that y must be 0. And in the second equation, y is equal to a over b, from this first equation, y is equal to a over b, and so equation 2 gives us a value. It says, well, y is a over b, and a is not 0 and b is not 0, so I can actually do that division, and we're left with this. So solving that, we must have m minus nx. I don't know why I write it backwards, being 0, and so x must be m over n. So there are two equilibrium values. In this case, the equilibrium value is 0, 0, and in this case, the equilibrium value m over n, comma a over b. So those are our equilibrium values. Let's draw a picture where we show those curves, and I'm going to redraw this on the next page. Here we are with our setup. We've got our differential equations, we've got our equilibrium values, and I'm going to start by rearranging those differential equations a little bit. I'm going to factor out the b. So if I factor out the b, I'm going to put a b out the front, and so this, what was an a there, is now going to be a divided by b. So I'm going to delete that and write a divided by b, and then I'm getting rid of the b there. And if I do a similar thing here, I'm going to factor out the n, and what I'm left with is m over n minus x. And I took the n out the front. And in this case, and the advantage of that is it lets us see exactly the sign of this quantity. So let me show you what I mean. One of our equilibrium values is at 0, so we've got an equilibrium value down here. And the other equilibrium value is when the m value is equal to, the y value is equal to a over b, and the x value is equal to m over n. Now I don't know what those values are. I know they're positive because a, b, m and n are all positive. So we're up here in the positive part of the axis in the first quadrant, and x and y are the number of fish, so that's definitely a positive value, right? Because it's actually a population value. And so we have these special lines, right? These are the same sort of lines I was drawing last time. This is y equals a over b, and this is the line x equals m over n. And the reason I'm drawing these is because these are the values that make one of the derivatives 0. So we've got, let me mark it in even brighter color, we've got an equilibrium value there, and we've got an equilibrium value here. Right? So the x value is m over n, the y value is a over b, that's an equilibrium value. But if any of those things are 0, then the rate of change is 0. And that includes when x equals 0, so there's something special going on when x equals 0, and also when y equals 0. So what I'm doing here are taking out the factors of these things, and I'm saying what happens when there's 0? Right? There's y equals 0. It's one of the ways that this term can be 0 from there. And then there's x equals 0. That's one of the ways that dx dt can be 0. So I've marked all of the important curves on here. Those are exactly the values of x and y that gave us these equilibrium points to begin with. And now we work around them in the picture. So I'm going to go around to each region and look at what's happening. If I'm in this region over here, then just looking at the y value, I'm above this y value, a over b. So over here, y is bigger than a over b, right? But also x is bigger than m over n. So if I'm in this region here, x is bigger than m over n, y is bigger than a over b. And if I know those two things, I can go over here and work out derivatives. X is always positive because it's a population. Y is always positive. It's a population. M and B and A and M, they're all positive. But these things in particular that I drew in the blue box are positive. They're always positive. They have to be positive. So the only way these rates of change can be negative is if this term in the bracket's negative. So really I can ignore these blue boxes because they're always positive. Okay? So the sign of the rate of change is given by this second bracket. Now if I'm in this region, the y value is bigger than a over b. So I've got a over b, I was subtracting y. Y is bigger than a over b, so this must be negative, and that means x is decreasing. Right? This is negative, that's positive, so the rate of change of x is negative, we're moving to the left. Going over here, the x value is bigger than m over n, and so m over n minus x, well that's also negative, and so the rate of change of y is also negative, and so y is decreasing. Let's go over to this region. The region over here, we have x now less than m over n, right? Because here's m over n, and this x value, whatever it is in this region, is going to be less than that. But the y value is still above that line, a over b. The y value is still positive, well, still greater than a over b. And so now using that information, we can go and we can draw these pretty little sort of indicators. What's going to happen is that when x is less than m over n, we're taking m over n and we're subtracting a number less than m over n, so that is a positive number, and so y is a positive times a positive, which means y is increasing. For the x value, my x is still bigger than a over b, so the x value is still decreasing. So we have that kind of behavior. And we just go around and we do this for each region, right? In this region, I'm thinking about, and I should say that I've got x greater than 0 there. In this region, I've got x greater than 0 but less than m over n, and I've got y greater than 0 but less than a over b. Right? That's the region we're in. There's the region y is between 0 and a over b, and the region where x is between 0 and m over n. So what happens? Y is less than a over b, so this is positive, so x is increasing. X is less than m over n, so this is positive, so y is increasing. Getting the idea here? What happens next? In this region, we've got x is still bigger than m over n, but y is between 0 and a over b, and so we can just, we can start thinking about this. All we did moving from here to here was change the x, so that could have only have changed the rate of change of y, so the rate of change of y must be now going down. X must still be going to the right because x is bigger than m over n, and y is less than a over b, and therefore this thing is positive, so x is increasing, y is decreasing. And there is our beautiful little picture, which gives us kind of overall motion, right? This one's down and to the left somehow. This is up and to, this is down and to the left. This is up and to the left. This is up and to the right. This one's down and to the right. And now we've got to work out how to fit those things together. And one way to do that is also think about the special lines. Think about the line x equals m over n. When x is exactly equal to m over n, y is not changing because dy dt is 0. So the only thing that's changing is x. So on this line, I'm moving directly left and right. I don't know, I've got to work out which I'm doing, but my motion is entirely left or right. When y is bigger than a over b, the rate of change of x is negative, and we head off to the left. When y is less than a over b, the rate of change is going to be positive, and we head to the right. So that gives us an idea of what's happening. I can do the same thing here. What happens when y is equal to a over b? Well, then x doesn't change. dx dt is 0. And dy dt depends on the x value. If x is bigger than m over n, then y is decreasing. Right? And you can see that it has to be decreasing. It's decreasing here, the y value. It's decreasing here, the y value. I couldn't draw it going up here, or it would conflict with the picture I've got. That argument means it's got to be going up here. When x is less than m over n, this thing is positive, so y is increasing. So this should give you an idea of kind of how this flows. There's two other lines I could draw. When x is equal to 0, that's this line. When x is equal to 0, x doesn't change, but y does. So along this line, we're either going straight up or we're going straight down, right? And in this case, x is 0. So going to this thing tells me that y is increasing, so we're heading up. And similarly along this line, when y is equal to 0, x is not, x is the only thing that's changing. When y is equal to 0, x is the only derivative that's not 0. And when y is equal to 0, this term drops out. Everything else is positive, so x is increasing along the line y equals 0. So hopefully you can see how this stuff would fit together. Stuff is flowing out of this. So we've got this equilibrium value here, right? This equilibrium value is 0, 0. Stuff is flowing out of it, right? Stuff goes straight up that line. It goes straight to the right here. The only way to make sense of this, any point in this region must be going up and to the right. So the only way to make sense of this is going up to the right, but when I get to this line, I have to be going straight up, right? We're going straight up at that moment, and then I must be going up but to the left. So the only way to make sense of this is to imagine that curves are looking something like that, because I can't cross this line, right? This line here is going straight up, and I can't cross these trajectories. These are trajectories and they can't cross because they're physical. Right? If I start with 0, if I start down here with 0, whatever x was, trout maybe, then the bass population just grows, right? Because this is literally the number of trout along this way, and this is the number of bass along this way. So if I start with 0 trout, I'm right here, then the bass population just grows. All right, so imagine though that I go off to the right, but I'm going this way somehow. Eventually I might get to here, and again I have to be going straight across when I get to this point, but then I've got to be going down, but again I can't cross that line down there, so the population must somehow level off, or at least asymptote down here towards, it asymptotes down here towards 0y. And somewhere in the middle there's going to be some curve in the middle that goes straight in there, right? And that kind of forms a dividing line, because you can see a similar behavior here. I'm going to have curves here that come down, go straight through, and then head off to the right. But I'm also going to have curves that come down here, oops, too soon. They come down here, level off, and then go up to the left like that. And then somewhere in between, there's got to be a special case that goes straight down the middle. And here there's got to be a special case that goes straight up like that. And here there's got to be a special case that divides it and goes straight that way. And depending on where I start, I'm going to get a whole bunch of trajectories that have this kind of flavor to them. And if you think about these are the only ways that I can kind of match up the arrows that I've drawn in a consistent way. So some of them are going to go real close up there and then head off to the right. And some of these are going to really hug that line for a while, but then eventually they're going to have to zoom off that way. So these give you an idea of how the population is going to grow. And all of this comes from looking at that differential equation and doing an analysis. Isn't that awesome? All right, so what's our conclusion here? We've drawn these trajectories. How are the populations actually going to behave? Remember, we have two equilibrium values. We've got the equilibrium down here, and we can look at that and we can see that this equilibrium is unstable. No matter where I start, all of the trajectories move away from it. So that equilibrium at the point 0, 0, it's unstable. Every single trajectory moves away. There's a trajectory, trajectory that just moves off along the x-axis, right? That's one of the trajectories. There's a trajectory that heads straight up the y-axis. That's one of our trajectories. But everything is moving away from the origin there. And so that's an unstable fixed point, an unstable equilibrium value. What about this one? What happens to this one? Well, if I'm on this curve, I'm going to head in towards that equilibrium value. And if I'm on this curve, I'm going to also head in. If I'm on these curves, though, I'm going to be moving out from the equilibrium value. So there's two very special points here, two very special curves that will take you to this equilibrium value. But the chances of being on one of them is so tiny, because that's a very special curve. If I start just a little bit off that curve, then I'm going to run along that curve for the longest time. But eventually, I'm going to go whoosh and head off this way, right? So even if I'm really close to that curve, I'm going to miss the equilibrium and go shooting off. And so this is essentially an unstable equilibrium. So you will never, in general, end up at the equilibrium m over n, a over b. Because, I mean, there's a couple of very special curves that will take you there, but if you start with a general point nearby, you move away. And that's what I want for stability. For a stability, I want to be able to take a point nearby and have it move towards that point. Whereas in this case, a point nearby is going to move away. In fact, points far away might actually move in, but then they move away. And so that doesn't meet our definition of stability, which is when you're near the point, you get closer over time, not further away. You never move further away. So we've got two unstable equilibriums. What does that mean about this system? Well, think about all of the trajectories that start down there. Like I said, there were those two special lines, right? The two special lines, and probably there's a line that's joining through that equilibrium and then runs up there. If you can kind of see my horrible scribble there. And then there was a trajectory up here, and there may be straight lines, I actually just don't know. There's a trajectory of some kind that must have this kind of behavior. So it gives us a X kind of shape. If I'm in this region, then eventually all my trajectories are leading me up to this axis. They're all going up, and they're all going to asymptote going upwards, because I can never cross the line x equals 0. So they're all going to asymptote up towards the y-axis up here, which means the x value is going to 0, which means the number of trout is going to 0, which means we're heading up the y-axis. That means the number of bass is going to infinity. Let me just check. The y-axis is the number of bass. So as we head up the y-axis, the number of bass goes to infinity. So if I start in this region, the trout die out and the bass take over. Obviously, this is a small pond. It's not going to go to infinity. Our model didn't take into account that there might be a limited population capacity. If we wanted to do that, we could change the model to include logistic growth where we have a carrying capacity. Look at the homework. But in our case, this goes off to infinity. What happens if we start up in this region? Any of the points in this region will eventually also head up the y-axis. Because even if they start really close to that red line, they eventually whoosh up towards the y-axis. So in fact, anything on this whole side of the picture, I'm running out of colors, anything on this whole side of the picture will lead to the trout dying out. So this whole side of the picture is where the bass win, right? In this, anywhere I start on that whole picture, anywhere from that horizontal line, that's not horizontal, that's diagonal, anywhere from that diagonal line to and above, the bass are going to win. But on the other side, down here, the trout are going to win, right? If what we mean by win is the other species die out. Because every single starting point, every single initial value in here is going to end up trending along the x-axis eventually. Even if you're starting up here, you're eventually going to end up trending down towards the x-axis. Towards the x-axis means the number of trout is going to infinity and the number of bass is going to 0. So, back to our original question. Here's the setup. I redrew it a bit more nicely so you could see it at once. On this side of these kind of red line, the bass win, right? The bass survive, the trout die out. On this side of that line, the trout win. The bass die out and the trout just breed and breed and breed. And so there's no way here, unless you happen to start on this really special line here, or this really special line here, unless you start with those two lines and move directly into that equilibrium value at the center, unless you start there, there's no way to have both species coexist. Because on this whole side of the picture, the bass die out. And on this whole side of the picture, the trout die out. What do I mean by die out? Their values are going to 0, right? All these curves are moving up here to the left, right? Because that was our picture. Everything in these regions moves up and to the left. And so up and to the left means x is getting smaller forever, which means x is going to 0, and y is getting bigger forever, which means y is going to infinity, which means the trout are dying out. And similarly on this side, the bass die out. The y values are going to 0 in all of these curves. And so this simple model lets us answer the question, can these species coexist? And the answer is, no, they can't. Or perhaps you might say it's not very likely, because there are really special values that may suggest that you could do that. But remember, this is a mathematical model. I'm not going to be able to get a whole number of fish on these curves necessarily. And so even if this is an integer number of fish, I can't move smoothly down this curve because the number of fish is not really a continuous variable. We've made approximations here. So just because this is maybe 5 trout and 7 bass lies exactly on that thing, on that point, I can't smoothly just slide down there because I can't have 3.7 bass. Right? So in reality, this curve is probably completely unobtainable. So our answer to the question is no, the species can't coexist because either one or the other dies out. And our model would allow us to estimate which one would survive, right? Because based on the values of m over n, at the very least we could estimate that this line here is a line with a slope, because we know that this is the origin and we know that this is the point m over n comma a over b. So we could look at that slope, we can get the slope of that line, and if you give me an initial value that starts above that line, my model suggests, and I'm guessing that line is exactly a straight line, but the model might suggest then that the trout die out. Whereas if I start below that line, the bass are going to die out. So the model gives us some insight, but most importantly, it answers the question, can they coexist? And that answer is no. And it's a cute little model to work with. So we're going to look at another one of these next time. Have a look at some of the problems. They'll show up on the next homework sheet. I hope you're doing well. Give me a shout if you have questions and have a wonderful day. Bye.